Hi everybody, my name is Lorenzo. Thank you for the invitation for coming here today. I'm a mechanical engineer and PhD candidate from the University of Genova, Italy, sponsored by the Italian Institute of Welding. And in the past 6 months, I visited the Center for Digital Engineering and Manufacturing at Cranfield University. I collaborated with the center group dedicated to develop a digital twin demonstrator for a household wind turbine. I'm specialized in computational fluid dynamics CFD simulations for turbomachinery. And regarding my research, I use my time at Cranfield to develop a strategy and methodology that aims to optimize the operational efficiency of a turbomachinery asset to prevent costly failures when in presence of sensor malfunctions. Sensor malfunctions that in this scenario can lead to faulty data. And as we know, faulty data can misguide controls actions, thus accelerating wear, overheating, or imbalance, or leading to the imbalance in worst case scenarios of the asset. So in other words, and in simpler words, from sensor inaccuracies through a cascade of failures, we could land into a costly and planned downtime. As I said in the introduction, my case study was a small-scale wind turbine, and I focused on a type of fault that is present, can be present in large-scale wind turbines, which is yaw misalignment. In simple words, yaw misalignment means that the wind turbine rotor plane is not fully perpendicular to the incoming wind direction. And of course, if this happens, it means that turbine will not harvest as much power as possible. And in this scenario, the fault is caused by faulty data readings coming from the wind vane sensor, highlighted here with a yellow arrow. So at the center, we try to replicate a yaw system that tries to emulate large-scale wind turbines. And in real life, the yaw misalignment could be caused by faulty readings. For example, if due to environmental conditions, the sensor is hit by a hailstone during a hailstorm, and from that moment on, it will present an offset, show an offset in its readings. And because of this, it would drive the turbine towards a different angle with respect to the true wind angle. Or maybe after a maintenance operation on the asset, the sensor could go miscalibrated. So to tackle this type of fault, I first detailedly studied the aerodynamic behavior of this specific wind turbine model in presence or not of yaw misalignment, different degrees of yaw misalignment, and thus evaluating the power production, the expected power production from the turbine. Digital twins can serve as the optimal solutions to tackle this type of faults and to guarantee the operational efficiency and the integrity of the asset, thus improving the resilience of the asset. And the novelty that comes with this approach is the introduction into the digital twin architecture of computational fluid dynamics simulation results, meaning I populated a performance space for this specific wind turbine in presence or not of different degrees of yaw error, and evaluated the power production. And these results are fed and recalled into the digital twin architecture, and they are interpolated also through the information provided by other sensor data, and an offset is detected. And if a specific offset, yaw misalignment offset, is detected and goes over a certain threshold fixed to 5 degrees, then a right time automated feedback, it's applied through the yaw system on the turbine to realign it with the wind direction and harvest as much power as possible. To conclude, from that moment on, if the offset is detected, the readings from the wind vane sensor, the faulty readings, will be ignored. Here in this slide, I present you some preliminary airfield tests we ran at the airfield of the university. And as you can see, as a simulation of the digital twin algorithm I developed, where from the first instant, I set the sensor yaw angle to a complete different degree with respect to the true wind angle. And as you can see highlighted in red, the algorithm, by recalling CFD, is capable of detecting the presence of an offset set here to 15 degrees with respect to the true wind direction. And from that moment on, it will adjust, correct the angle, and avoid listening to the readings from the sensor, wind vane sensor. So as you might have guessed, there is no need for human intervention. Conclude, this approach could be scaled, applied throughout the turbomachinery scenario to other types of turbomachinery assets, let's say, leveraging the insights provided by computational fluid dynamics, ensuring the maximum operational efficiency possible for the turbomachine. We could go to and tackle other type of faults, such what we are doing now. We are starting to study the buildup extent to where we started to extend this methodology to another type of fault, that is the buildup of erosion on the leading edge of the wind turbine blades. But we could also be applied to other types of turbo machines, as I said, such as the fan of an aero engine. And this methodology can then bypass the reliability of faulty sensors, improve the integrity and the resilience of the asset. Thank you, everybody.
So Lorenzo, this one is for yourself. What was the simulation toolset you used to build this model?
Okay, thank you for the question. I used ANSYS Fluent and the high-performance computer provided by Cranfield University, and also developed the algorithm, digital training algorithm, through Python.
Very good, thank you. And a follow-on question for yourself. How many types of errors in total are you able to characterize from the turbine operability using the sensor readings so it becomes more resilient?
Okay, in this specific scenario, the errors are coming from just one sensor, the wind vane sensor, that understands the wind direction. And from that, the sensor readings drive through the yaw system. We have developed the wind turbine yaw angle. And so errors are coming just from one sensor. The others are working okay.
Our final question here, Lorenzo, for yourself is how do you fix the issues with data inaccuracy, and what techniques were used in this particular use case for bypass?
Okay, I cannot share a lot because the paper hasn't been released yet. So basically what we are doing is looking at the power extracted by the turbine. If the sensor is in a healthy condition, the power should be the maximum possible. And we know what the power is because we have CFD as a reference. But in a faulty sensor condition, if the sensor thinks to drive it drove the turbine to be fully aligned with the wind, but if in reality it is not, we will see from the turbine itself that acts sort of a sensor that the power is less. So we recall CFD, we see the power, the expected power, and if we see that there is less power than the maximum available, we can then detect the angle through an interpolation and see if we hit a certain threshold and thus apply the feedback. I hope it was clear.